Here's our object sitting on a surface. So here it is, sitting on a tabletop or something, or maybe this is maybe a little bit closer to that size. Let's imagine now I come along and I push it sideways. I push it to the side. What's going to happen? Well, it might move, it might not move, but there are other forces that are involved. Those are, what kind of forces? Those are frictional forces. So friction starts acting on the object. Let's take a look at my table. I'll focus down on my table and we'll take a look at something moving on the surface. Here's my table with an object resting on the surface. We know that, that this object has a weight of 13.7 newtons. That means there's a force acting down of 13.7 and then a normal force upward of 13.7. So we have a zero net force. Now, what if I come in and I start pushing it to the side? Let's imagine I push on it very, very lightly. I push with a very small force, let's say 1 newton. It doesn't move. That must mean that there's another force acting that way with a force of 1 newton. That force that way is a frictional force. It's what we call static friction. Static means, is the term we use when something is stationary, is not moving. What if I push on it with a force of 2 newtons? Well, still it doesn't move. So that must mean the static frictional force has increased to 2 newtons. What if I push on it with 3 newtons? It still doesn't move. Static friction has increased to 3 newtons. I can continue increasing my force, but eventually it starts to slide. When it starts to slide, the friction changes. It changes to a different kind called kinetic friction. So let's think about this. The value of the static friction can be small if I push on it with a small force. It can be larger if I push on it with a larger force. But there's a maximum value. Eventually, I will overcome that static friction and the object starts to slide. When it slides, a different kind of friction called kinetic friction starts to act. Let's take a look at what the forms of those forces look like. Here is my mass of 1.40 kilograms resting on a surface. We know the weight of the object is then mg, 1.40 times 9.8, giving us 13.7 newtons. So the weight of the object is 13.7 newtons. As long as there are no other vertical forces, we know that the normal force must also be 13.7 newtons to balance the weight. I'm going to come along and let's imagine that I push on this object. So I push it to the side. I'll push it with what we'll call F push. But let's assume that it doesn't move. We'll assume that it hasn't started sliding yet. What do we know? We know that we must have an equal but opposite force pushing back, which I'll call F sub s, lowercase f sub s, where F sub s is called the static friction. What's the value of the static friction? The static friction will have whatever force it has to have in order to balance the pushing force, up until a maximum value. We can't keep pushing harder and harder and have the object stationary forever. Eventually, the object starts to slide. That means that the static frictional force has a maximum value. We will write that as F sub s max. This is the maximum value for static friction. What determines how large that is? What determines the value of Fs max? A couple of things. The surfaces of the two objects. If they're very, very smooth surfaces, very slick, slippery surfaces, then we get less friction. It's much easier to move something if it's very slippery between them. Imagine, say, someone standing on ice. It's much easier to start them sliding than if they were standing on concrete or in grass or something like that. It would be much harder to start them sliding. So the two surfaces affect how much friction can actually be exerted. Also, the normal force how strong the push is acting on the object between the two surfaces. That affects how much friction there is. So if this were actually on a surface and I tried pushing on it, I could push with the maximum static frictional force would be one value, but if I were to push down on this harder, it would be more difficult to get it started to slide. It would be harder to get it to start to slide. So the Fs max actually depends on the surfaces and the normal force between them. We will write that in this way. Fs max is equal to, it's proportional to the normal force, so as an equality we'll write equal to the normal force. The constant of proportionality then is what depends on the two surfaces, and we'll write that as mu sub s. This letter is the Greek letter mu. Some people pronounce it mu, I'll pronounce it mu. And mu looks like the letter U, but with a tail in the front. And you write it with the tail and then the letter U. Remember, that's also the symbol that we used for micro. When we had micrometers, micrograms, it's the same letter, mu. Mu sub s is called the coefficient of static friction. The coefficient of static friction. And it depends on the two surfaces that are in contact with each other. Mu s is larger if there's a lot of friction. In other words, the surfaces are sticky or rough, something like that. Mu s will be much smaller if they're very slippery surfaces. We'll stick some numbers in just a second, but first let's imagine that we push hard enough. Let's imagine that F push is larger than the maximum value that we have for Fs max. What's going to happen? The object starts to slide. In that case, we have a different kind of friction, a sliding friction, and that is called kinetic friction. And the symbol that we'll use for kinetic friction is a lowercase f sub k. Typically lowercase f's for both friction, static and kinetic friction. Lowercase k for kinetic friction. Kinetic friction, the amount of kinetic friction depends on a number of different things. It depends on the surfaces. Again, slippery surfaces will have less kinetic friction. Rougher surfaces have more kinetic friction. It will also depend on the normal force between the surfaces. But it will also depend on how fast the objects are moving, how fast they're sliding against each other. It depends on the velocity. But for low velocities, there is not much of a dependence. So we will always assume that we are talking about low velocities. We will make the approximation that the frictional force is independent of the velocity. In that case, we can then say that F sub k, very similar to Fs max, equals the normal force with a constant of proportionality. That is just about the worst mu I've ever written. With a constant of proportionality of mu sub k, where mu sub k is the coefficient of kinetic friction. Coefficient of kinetic friction. Very, very good. Let's just go back over this. We've got an object resting on a surface, and for now we'll assume the surface is horizontal. The object has a weight that's equal to mg. With no other forces acting vertically, the normal force is equal to mg. We come along and we start to push the object with some force. We'll call it F sub push. What happens? If F sub push is small enough, there is a static frictional force that will balance F push, pushing backwards against the pushing force, that balances the pushing force to give us a zero net force, zero acceleration. The object remains stationary. However, if the pushing force is large enough, what is large enough? What does that mean? Large enough what? Larger than Fs max, then the pushing force overcomes the static frictional force and the object starts to slide. At which point the friction turns into kinetic friction, sliding friction, or friction of motion, and the value of the kinetic friction is then equal to mu k times the normal force. And then we can figure out what the net force is on the object, and we could determine the acceleration. Very, very good. Let's stick some numbers in here.